Answer for homework 11, question 2. So the question says that the following functions of V either represent an autocorrelation function of a Wide-sense stationary process by setting V equals to tau, a spectral density function by setting V equals to omega, or both. So the first example that they give is f of V is equal to e to the negative absolute value of V. And so when we sub in tau, we have f of tau is equal to e to the power of negative absolute value of tau, and that's also equal to e to the negative absolute value of negative tau, which means that the function is even. E to the negative absolute value tau is also less than or equal to e to the negative absolute value of 0, which means that the autocorrelation of tau is less than or equal to the autocorrelation of 0. And we also have, when you Fourier transform the function, you end up with 2 alpha over alpha squared plus omega squared, which is always positive. And so that means that that example can be an autocorrelation function. And so to see if it can also be a spectral density function, we have to look and see if the function itself is non-negative. And so when we sub in omega for V, we have f of omega is equal to e to the negative absolute value of omega, which is always greater than 0, which means that it can also be a spectral density function. So basically it's both. The second example that's provided is f of V is equal to sine squared V over V squared. And so when you sub in tau, you have f of tau is equal to sine squared tau over tau squared. And that is also equal to, because you're squaring both tau above and below, it can also be equal to sine squared of negative tau over negative tau squared, and so that means that the function is even. So this is a calc identity from Calc 1, where you have the limit as t approaches 0 of sine squared, as tau approaches 0, of sine squared tau over tau squared is equal to 1. So that shows that the function is also non-negative. And then when you Fourier transform this function, I just plugged it into a Fourier transform calculator online, you end up with this shape here. And so that shows that the Fourier transform is always greater than 0. And so because it's always greater than 0, it's always non-negative, which means that f of v equals sine squared v over v squared can be an autocorrelation function. And so when we look and see if it's also a spectral density function, you sub in omega for v, and sine squared of omega over omega squared can never be negative, which means that the function can also be a spectral density function. And so then the last example that's provided is f of v is equal to a piecewise function. So it's equal to 1 when the absolute value of v is less than or equal to alpha, or it's equal to 0 when the absolute value of v is greater than alpha. So when we check the first condition to see if this function is even, we see that the absolute value of v is equal to the absolute value of negative v, so that shows that it's an even function. However, when we Fourier transform this, we see that Fourier transform is f of tau, because we're looking at to see if it's an autocorrelation function. So it's f of tau is equal to 2 times the sine of alpha omega over omega, which can be positive or negative, which means it's not always non-negative, which means it cannot be an autocorrelation function. However, when we look and see if the function itself is non-negative, we have that it's 1 when omega is less than alpha, and we have 0 when omega is greater than alpha, which means that that is always greater than 0, which means that the function can be a power density spectrum function.